Good day, folks. Welcome back. And we have a package in from PCB Way. So these are the PCBs for my little project with the Joule Thief. As usual, we got a pen and a few stickers. We've been sending these monster stickers recently too. So let's have a look at these boards here. These are different stickers too, what we normally get. Alright, have a look at these boards. Yeah, so I went with white this time. Oh, look at this. They sent me a pile of them. 1, 2, is it 10 of them they sent? 1, 2, 3, 4. That's quite a few. 10, actually, no, 11. 11 boards. Cool. Yeah, I really like this effect. This is something I may do more often. I like the white with the black. That's nice. Very nicely done. So what I'm going to do, just give me a second here and clear some of the stuff out of the way. I'm going to get all the parts we need to build this up. As far as the transformer goes, that's involved in this. So we have this little transformer here. If you remember the schematic from the last video on this project, it's generally wound by the person building them. So like here's one I wound myself a few years ago. You just get a little core and you wind, 15, 20 winds around, and you wind both the primary and the secondary at the same time. You kind of just get a length of wire, bend it in half, and then start feeding it through. So you wind both primary and secondary at the same time. Now you can do that, or these actually I found these on Amazon. These are just little what they call them common mode chokes, and that's what it is. So, but you can use it as a transformer. So you got your primary and your secondary. You can see here they've wound them with a different color metal, or a different color insulation on them. So the dark and the light. And since they're the same number of turns, it doesn't really matter. I think these are about 20 turns, if I'm not mistaken. But I decided to just pick up a bunch of these from Amazon for this project because heck, winding these cores can be a bit of a drag. So basically, all you have to do in order to get your center tap here, so call this the center tap here, is to just take one side of the primary and one side of the secondary and connect them together like that, and that's all you need to do, and that is done for us in this board here. So, all right, so we'll assemble those up, and we'll see how they work. Oh, I've got to get some diodes. There we go. Get the iron turned on. Get the tip cleaner ready, and we have plenty enough solder right here. Okay, let's get started here, and we'll set the music going and speed this up, and see you at the end. I'll make up a little kit for myself that I can build up when I need to get some experiments done. But this is going to be enough for us right now. So I just need to get a shorting block to go across here. Alright, here we go. So we're going to put it down here, so we can light up that LED. And what we're going to light up the LED with, we have a battery holder here that is all ready to go. Alright folks, I found this battery here. Took this out of a piece of equipment a couple of days ago because it stopped working. There were the 2 battery device and it just wasn't working anymore. We got 1.38, well, call it 1.39 volts in it. And let's see if that can get our little Joule Thief up and running. So this here is a blue LED, and we know that 1.39 volts is not enough to light up a blue LED, but there you go. It's lighting it up nice and bright. So let's have a look at that on the oscilloscope. Okay, we've got our oscilloscope all hooked up. Let's just get it reading something here. We'll put it across the collector of the transistor, which is basically the voltage that we have going into the LED. So it's actually peaking up quite high here. Let me put this on DC coupling here. We're at 1 volt per division here. So it's actually rising up to a maximum of 4 volts, coming down and then dropping off. So this is actually here. This is the point exactly where the transistor itself turns off, and this is where you get the flyback. So I'll hook up another lead to this, and we'll have a look at the base voltage on the other channel. 1 second. All right, there you can see the base voltage. You can see where the base voltage actually goes negative with respect to ground, and that's when it really turns that transistor off hard and creates that flyback effect, which gives us our high voltage across the diode there. Okay, so what else can we use these for other than lighting up diodes that take almost 3 volts with a battery that has less than 1.3 volts? Well, let's move this jumper over. Move it over to the other position here. Now we've got fairly high voltages here. You can see that we're reaching up here for a peak of 53 volts on the collector, and that actually is exceeding the breakdown voltage of the collector emitter junction in the transistor. That's what's limiting that voltage. You would go higher if we used a different transistor. This actually would go higher. So for a very short period of time, it conducts right across back down to ground from the collector to the emitter. And here we have the base going negative 10 volts. That's a transistor and cutoff, I'll tell you. And so what are we getting on the output then? So if we move over here, have a look at the output of this. Let's change our trigger to the other channel here. So we're getting, if we look at the output, it's 20 volts per division. So we're getting, looks like about, it's over 50 volts. What happens if I put a meter across that? Would that load it down? Does seem to be bringing the voltage down a little bit, just having that there. But it doesn't seem like we're introducing very much ripple. We're just charging the capacitor a little bit. So yeah, we're getting over 50 volts on the output. That's pretty impressive for a battery that is at this point in time at 1.35 volts. Well, you could actually use this if you needed a very, very small amount of current at a high voltage. You could actually use this device here to give you 50 volts. And why are we limiting it to 50 volts? Well, like I said earlier, we're reaching the breakdown, the collector emitter breakdown voltage of that transistor. So that flyback peak, the peak of the flyback voltage, is never going to exceed that amount. But we can pump up this capacitor to that level, store it, and we get a constant 50 volts coming out of it. So let's put a resistance substitution box across that. Okay, so here we have it set up. I've got the scope now in AC coupling, and we're looking at basically the ripple or noise that's being produced across this output. So we're at 41.6 volts with 1 megohm across it. 680K, that's going to drop down, and of course the noise is going to get a little bit worse. The ripple is going to get worse. Let's change the time base on that a little bit. So you can see as we load this down more and more, we get more and more ripple. So there's 470K, and we've got, we're down to 37 volts. So if we do the math on that, getting about 80 microamps of current at this juncture. So let's go down to 100K here and see what kind of voltage we can sustain and what kind of noise we have. So I would say we're bordering on 250 millivolts of noise. It's okay, but now we have 27 volts. It's giving us 270 microamps. So if that's the your requirements for very low current, then you can actually build a high voltage supply. Well, high voltage, we're not very high anymore, but we're up to 27 volts from a battery that's at 1.3 volts. So all in all, that's pretty useful for certain applications. So it's more just a little toy. It could be an actual high voltage supply for you. Now, if you, like I said, if you use a better transistor than this, something with a much higher breakdown voltage, you could get a much higher voltage out of it. And indeed, if you wanted to use a good fresh battery in there and just use this as a high voltage source, then you could actually design one of these just to do that. And you can see here, it's not all that noisy. I mean, we've had a look at wall warts and stuff like that produce a heck of a lot more noise than this. So you can build a pretty good, reasonably high voltage supply with it that's powered off a small single battery. All right, and there's something else you could do with it. Now, let me clear some of this stuff out of the way here. Yeah, a couple of videos, or one video ago, I showed you this. Asked you if you knew what it was. Some people did, some people guessed it right away. It is a Joule Thief being used to charge up a battery. Lithium ions, 18650 cell. And it does that. Like when I put this cell in here, it was down to 3.1 volts. And I think now, last time I checked, it's up to like 90% of its charge. It's up to almost 3.9 volts. Now, is it very practical to do this? No, it's not. It's so far it's taken 3 almost dead batteries. Now, what's this one down to here? 1.25 volts. So it's taken 3 batteries of about that voltage to get there. But the thing is, it gets the voltage up fairly high, fairly quickly. So one of these batteries has got at 1.3 volts, it's still got over 50% of its energy in it. So if you can get that energy out and transfer it into here, then you reduce the time it takes to charge these batteries. But one thing it does, it appeals to my sense of protecting the environment. I just hate to throw these things out with half their energy left in them. I mean, it just doesn't make sense to me. You buy the battery for a purpose, sure, but you're paying for that energy, right? And you're only getting to use maybe half of it. This Joule Thief will get these all the way down to 0.5 volts. So it went down from about 1.2 or 1.3 volts down to 0.5 volts. No, it's not practical. It's not practical at all. But it makes me feel better about dumping a battery once it's down to half a volt rather than dumping it at 1.3 volts. So yeah, and that's what we can do with this one here. We can, just attach another battery holder to it and pop an 18650 cell in there, and away you go. Now we're charging up this battery. Now this one's already at 4.1 volts, so we're not going to charge it up very much. But I did want to have a look at what the curve is on the collector here when we're doing this. Here we go. Let me set up the oscilloscope a bit better. Yeah, so we see here, okay, we've got 4.8 volts peak to peak. Across the collector of the transistor, there is enough voltage to charge this up a heck of a lot more. So right now this battery is charging, even though it was at 4.1 volts before, it's going to charge it up. Now the maximum I could charge this battery up to, I think, is 4.2. So I don't want to exceed it too much. You could consider this battery fully charged at this point. We're 4.38. You come back in a couple hours, it might be up to 4.139. That's something of that effect. But maybe that's not the point. It's not the point to you're not going to save any money. The point is not throwing these away. So what I'm actually going to do is I'm going to use one of these modules. That's why I wanted to build up the other one, because I want to frig around with it to see if I can make it even more efficient. And I'm going to take a whole bunch of these battery holders here. So a C cell size, a D cell size, an A size, and a AAA size. And I'm just going to put them all on one of those. I got piled to this orange plastic here. So I'm going to make a bigger one of these. So I can use any size dead cell to start charging batteries. Crazy, eh? And yeah, so that's a project for the future where I'll put that together. I do like that black on white though. That's pretty nice. I'm gonna use that more often. And so that's all I have for you today, folks. If you've got any questions about Joule Thieves, or if you have any suggestions about how we could make it more efficient, leave them down in the comments. Mostly just for fun and for interest's sake. But there it is, a Joule Thief, a perfect example of a blocking oscillator and how it works. See you in the next one, guys. Thank you.